read is required. So after the session, okay, you will receive the original paper on UNet architecture. Actually, the architecture looks very intimidating. Okay, it's like it has a two component. Compression path and expansion path. Your pre-trained DL model can be utilized once again. I can use it as a regressor, right? And again, regressor, there are two variations. 1x1 scalar regressor, or I can say a pre-x1 vectorized regressor, isn't it? Number two, classifier as a classifier. Again, within the classifier, binary or multiclass. I'm not marking that variation. What is about the third usage? Any idea? Can you suggest?
Generator.
Very good. Generator. Any other variation? If you wanted to use as a generator, how you can justify? If I wanted to use it as a generator, that's what. But I have not explained this. Did I explain this or any context that I told you?
Yes, sir.
Rashid, do you have any idea?
No, sir. I'm just thinking.
Classifier, or one more terminology, let me write here. Discriminator, right? Both are same, right? Discriminator. You can use a pre-trained architecture as a classifier or a discriminator. You can use it as a generator. Generator means, okay, you are going to get an output in the form of an image. Your output is going to be a tool. That is the meaning of generator. There could be a slight different way I can design this generator. Okay. If you wanted to create an output like an original image, okay, that is the generative AI that we'll be discussing towards the last component of our course. Okay, the last few sessions on the generative AI models. Generative AI models. So since our content is focused on the object computer vision context, this generative AI you will be seeing, of course, a large language model also we will be using like generative AI concept, like a pre-trained large language model act like a generator. Suppose you give some keywords, it is going to generate some paragraph of the text as a generator. So that is also a generative AI model. Okay, to the context of the text data. But here we'll be using the CNN based deep learning architecture as a generative AI model to the context of producing the output image. My intention is to create some output image. Okay, realistic looking output image. Let me write this as a grayscale, actual grayscale, or even a colored format also. Okay, grayscale format or a colored format. RGB. What I really wanted to highlight here is, because in the interview, many people I have noticed that they confuse between generator and the feature extractor. That's why I wanted to make this thing very clear. Because the generator, we have not seen any example for the generator, but feature extractor, we have seen some example, right? Even in the bounding box regressor, we have utilized till the last layer of the CNN layer. And from the last layer, we have designed the dense layer as a bounding box regressor. And do you remember in the image captioning exercise we used as a feature extractor? Your foundation module, one of the exercise we worked on the image captioning. Your input image, what we have done, we used some pre-trained model. Your pre-trained model, I'll be using the last layer. The last layer you can tap just before the last but one layer. Suppose if I use the VGG16 architecture, I know what is the last layer. My last layer is 1000 cross 1, which is a class component. If I just throw this, I use the VGG16 architecture till 4096. If I'm going to tap it, I'm using a pre-trained deep learning architecture as a feature extractor. Okay, now you are extending this idea. Now, are you clear about feature extractor? Isn't it? You know very well how you can utilize your pre-trained model as a feature extractor. Either you can tap this layer and you can show this as a one-dimensional feature vector, or even you can access the last layer of the CNN layer as a, in terms of a feature map also you can utilize it. According to the context, you can play around it. Say for example, in object detection, what YOLO algorithm has utilized inside it, they use up to this as a backbone. Up to this, they used as a backbone. From the feature map, they applied, if only the backbone and the head components are there, backbone will generate this feature map, and the head component is going to apply the anchor boxes and it's going to learn from the feature map, isn't it? Whether it is an object, whether the features, this is the edges of the person or edge of the car or edge of the truck. According to the context, either you can tap this portion and you can utilize as a feature extractor, or also I can also tap this information. If I wanted to embed this as a feature value for the image captioning application, we have taken this 4096 feature vector. I have taken this 4096 feature vector. I have concatenated with the sentences, right? English sentences. The girl playing in the beach. Okay. We have passed the sentence to as a language model to the LSTM model. The LSTM hidden LSTM unit output. That units we have taken and we have concatenated this. And we have created this as an image captioning application. According to the context, it's up to you, the feature extractor, whether you wanted to tap this two-dimensional space, or you can navigate till the dense layer and take the last dense layer. Actually, your original feature is flattened and it is mapped on hidden layer 1, hidden layer 2, and you are taking the last layer. That is a transformed version of your feature. You are tapping this as a 4096 feature vector. My application contexts are different, isn't it? Either you can tap this guy or you can tap this. Both I'm utilizing, I'm leveraging the pre-trained model as a feature extractor. Is it clear to you up to this? According to the context, either you can tap the last CNN layer or you can tap the one-dimensional last dense layer. But you should not tap the last output layer. Any question? But this process, this process itself not a generator. Okay, your feature extractor is different from a generator. Can I use this? Can I use a pre-trained model? Try to answer this question. Can I use a pre-trained model, several stage of a CNN layer, max-pool layer? If I tap the last CNN layer, this last CNN layer, if I tap, I'll be utilizing this pre-trained model as a feature extractor, isn't it? I cannot claim this last layer as a generator. Can you tell me the reason why? See, whatever we are discussing, it is a foundation for the next problem. With this foundation, if you understand the unit architecture, it's very simple and straightforward. You can easily navigate it. For that, you should have a clarity between when I can use my deep learning architecture as a feature extractor, what context we are going to use it as a generator. You try to understand my question. I have already defined the meaning of generator. Okay, let us don't worry about the internal architecture of the generator. I have given what kind of output generator is going to give me. Okay, but I have not yet thought about what is the internal idea of the generator, the building block of the generator. We have not discussed. We have not yet discussed. Even we have not seen any generator model in our foundation track also, isn't it? We have not seen any architecture as a generator. Only in the advanced model we are going to see a generator kind of architecture. But based on the context here, what is the use of the generator you are aware of, right? Generator model, I can use it to produce two-dimensional images. It looks like the original image, like a grayscale image or a color image. By understanding the usage, can you try to answer this question? Why don't I use a feature extractor model as a generator? Why don't I climb it? Hey, I can use the last layer of the CNN. Can I climb it like a generator? Why not? I should not climb it like a generator. What is the reason behind it? I hope by this time you understood the question. Are you there?
Yes, sir.
Yes, sir.
I got the question. The last layer of the CNN is the transformed version of the original raw image. I don't know how it will be considered as the 2D image of which will be the generated output. I don't know.
Okay, actually, what this 2D matrix reflects? Can you tell me what does this 2D matrix reflect?
It's a filter response.
Of course, a filter response. How it will be? Can I consider the filter response as the original gray level? Can we consider the filter response as the original gray level of the image? See, imagine if there is an apple. Okay, my filter response will be high only to the edge of the apples. Okay, my filter response will be some high value. Okay, let us not worry about this value. Here it gives me the value 15. Here it gives the value because the ReLU operation we do. A ReLU operation will retain the positive value only. It yields 10. It yields 22. This yields 36. This yields 15. High value, high value, high value, high value. So when I try to visualize this like an image, you get a feel of these are all the brighter pixels. You get a feel of an edge, a brighter pixel. All these responses we got a 0 response. Inside region also 0 response because the inside portion also is the skin of the apple. I just want only the shape of the apple. Actually, your feature map is going to describe the shape of the apple as some high response. What I mean to say here is this response, this value, it is not equivalent to the intensity of the apple, isn't it? This value is not the gray level of the apple. It is some filter response. That's all. I am leveraging the filter response to understand the feature map. Even I don't mind utilizing this as like I can simply threshold this feature map to keep it as a 0 background, and wherever the objects are there, I just keep it as a 1. Still, it will make sense, isn't it? Still, it will make sense of it. So my edges are being highlighted as these value, a non-zero response. Wherever I have got a 0 response, there is no edges. Only I have a non-zero responses. My edges are being trapped. So basically, this 2D is nothing but your feature map, right? Your feature map is not what you need to understand here is your feature map is not equivalent to your original image. Do you agree with this? Your feature map is not equal to the original image. Your feature map reflects some edge informations about the images, but that feature map itself, it is not equivalent to the original image. Can you try to comprehend the meaning of this? If you have any question on this, feel free to ask. You should have a thorough clarity on this before we jump into this. Can you able to comprehend this point? Why I'm saying that feature map is not equal to the original image? Penny, Larry, clear?
Yes, sir, I'm getting it, sir. Actually, each response of anyway, multiple filter we are using out of CNN. So each filter response will give you some kind of angle impression or some vertical posture or something. Collectively, even if we aggregate that, collectively we won't get it the raw image. Yeah, I got it, sir.
Because in the original image, you have the actual gray level actually, or 150, 152, 160 like this. When we are applying some masking operations, okay, this is your kernel. Just for illustrative purpose, I use a one dimension, but literally it's a two dimension. Okay, two dimensional kernel. You have the original intensities are like 65, 117. When you do a sum of products over this, I'll be getting only the filter response. That filter response, some number, numerical value I'll get. Okay, that number itself, it is not equivalent to the original gray level. That is the point. As simple it is. I get some number, right? Because these are random weights. These are randomly initialized weights, which is we call it as a kernel coefficients. When you do a sum of products with these random weights, you are going to get some response, and you are going to move the mask. Then I'm going to move the mask. Next, I'm going to get a next filter response. Next filter response. Those responses will not be treated as my original gray level. Point number one. Is it clear? That's the point. First point you should understand. My filter response is not equal to the gray level. Okay. Like the way we do convolution. Okay. I can retrieve my original image when I do inverse convolution, or I can call it as a deconvolution. One of the key steps I'm going to do is the deconvolution process. If I do the deconvolution process, okay, from the filter response, if I do a deconvolution process, I try to retrieve the original image. I'm trying to retrieve the original image. So in the next session, I'm going to start with how the deconvolution is going to work and how this deconvolution is related to our unit architecture. Okay, our unit architecture, just to as a catchy term, they have formulated this idea, but otherwise there is no specific reason, because the architecture, if you look at the original paper, let us don't worry about whatever the architecture inside this. Okay, I'll be starting from the scratch. But try to understand, I'm going to break the entire unit architecture. Even this architecture could be defined a simple, the first layer of the CNN, next to CNN layer, next to CNN layer. And again, this portion also, it is going to have a series of CNN layer. Okay, it's a series of convolution layer. Even they could have designed the architecture like a simple horizontal pattern. They could have drawn the architecture. But naturally, when you look at the architecture, okay, the CNN layer, as you move down, the size of the images is actually using small size, it is growing into a small dimension. So like a matrix size, when I draw a matrix size, okay, a smaller size from the smaller size, again, using a deconvolution, okay, the reverse plot, I'm going to retrieve this. So naturally, this portion looks like a U-like pattern. That is why they named as a unit architecture. Okay, nothing any special name for special meaning attached to the name unit. So, but you should understand what this portion of the CNN layer is doing, what this expansion path of the CNN is doing. So the compression part of the CNN, it's going to work as a feature extractor. Okay, the expansion path of the unit architecture is going to work as a generator. By the end of the today's session, try to just you remember the terminology alone. You just remember what are the building blocks to generate. Already, you know how a deep learning architecture can be designed as a feature extractor. You are familiar with. To understand as a generator, you should understand the process of deconvolution process. You're going to understand the deconvolution process. How the deconvolution process can be treated as a generator. Because at every stage when I do the deconvolution, I'm trying to retrieve back my original pixels. Because this guy will give me the feature map. From the feature map, I'm reconstructing. With what context we are reconstructing, that is the agenda. I'm just giving a very outline picture of the unit architecture in which we use it for the semantic segmentation. But we'll break down the architecture. What is being discussed in the original paper, I'll be discussing in the next session. Meanwhile, the original paper will be shared with you. Okay, let me show you the original paper. Just you try to see the building block and try to comprehend, because the very simplest paper, one of the simplest paper, don't worry, there is no too much technical jargon. This, if you come with a pre-read, even you can Google and download the unit paper. If you download for this unit paper, this is the original paper. It is published in May 2015. A convolution neural network for biomedical image segmentation. And look at this. It looks like a shape of this portion is a. This is what the contraction portion, and this is an expansion part. This portion acts like a feature extractor. This portion acts as a generator. Okay, what is inside this? What is happening and all? Don't worry, I'll explain. Okay, even though I'll explain it, but try to read this paper. Try to read this paper at least once, so that you can easily you're comfortable following this when I discuss. No need to read the complete paper. Okay, no need to read the complete paper. At least how do they this block, how they try to explain this block. Primarily this introduction part. This introduction chapter alone you can read if you can comprehend. Up to this. Yeah, up to this. Okay. This is the first page, abstract. First page, introduction, block diagram. This is the second page. And this is the third page. These 3 pages you try to